The world was a small, knowable place. At its center sat the earth, solid and unmoving, created by God as the stage for human drama. Above it rotated perfect crystalline spheres carrying the moon, the sun, the planets, and finally the fixed stars, all set in motion by the prime mover. This was the universe according to Aristotle and Ptolemy, a vision that had dominated Western thought for nearly 2,000 years. It was elegant, it was comforting, and it was completely wrong. Between 1500 and 1700, this ancient edifice of knowledge would be systematically dismantled by a series of brilliant, stubborn, and often courageous individuals. They would use new instruments, new mathematics, and a new way of thinking to reveal a universe far stranger, far larger, and far more magnificent than anyone had ever dreamed. This intellectual earthquake, known as the scientific revolution, did not just change what we know, it changed how we know. It created the modern mind. The revolution began not with a bang, but with a book published on the author's deathbed. In 1543, the Polish cleric Nicholas Copernicus released On the Revolutions of the Heavenly Spheres. Its central argument was heretical. The sun, not the earth, was the center of the universe. The earth was merely a planet spinning on its axis and orbiting the sun like all the others. Copernicus offered this heliocentric model not from new observations, but from a desire for mathematical elegance. The complex system of epicycles used to make Ptolemy's Earth-centered model fit observational data was, to him, a monstrosity. His sun-centered system was simpler and more harmonious. Yet Copernicus was a revolutionary who feared revolution. He dedicated his book to the Pope, and his work was largely ignored for decades, seen as a mere mathematical hypothesis. He had planted a seed, but it would take a century and better evidence for it to sprout. That evidence came from the most unlikely of places. A Danish nobleman with a metal nose. Tycho Brahe was not a theorist, but the greatest observational astronomer the world had ever seen. Funded by the King of Denmark, he built Uraniborg, a magnificent observatory palace, and for over 20 years he meticulously recorded the positions of the planets with unprecedented accuracy, all without the aid of a telescope. His data was his legacy. When a bright new star appeared in the constellation Cassiopeia in 1572, Tycho proved it was located far beyond the moon, shattering the Aristotelian doctrine that the heavens were perfect and unchanging. He proposed a compromise model of the solar system, but his true contribution was the treasure trove of data he would leave to his brilliant, difficult assistant, Johannes Kepler. Kepler was a mystic and a mathematical genius who believed the universe was constructed according to geometric harmony. Armed with Tycho's precise data on Mars, he tried to fit its orbit into circular paths. He failed. After years of painstaking calculation, he made a leap that would forever change astronomy. The planets do not move in perfect circles. They move in ellipses, with the sun at one focus. This was his first law of planetary motion. His second law showed that planets speed up as they approach the sun and slow down as they move away, sweeping out equal areas in equal times. Kepler had found the mathematical blueprint of the solar system, replacing the perfect circles of the ancients with elegant, if imperfect, ellipses. He had discovered how the planets moved, but not why. The question of why would be answered by an Italian who turned a toy into a scientific instrument. In 1609, Galileo Galilei, hearing of a Dutch invention that made distant objects appear closer, built his own telescope and pointed it at the night sky. What he saw shattered the remaining pillars of the Aristotelian universe. The moon was not a perfect smooth sphere. It was covered in mountains and craters, a world like our own. Jupiter was accompanied by 4 moons that clearly orbited it, not the Earth, a miniature solar system in itself. Venus showed phases, like the moon, proving it orbited the sun. The Milky Way resolved into countless individual stars, revealing a universe of staggering scale. Galileo published his findings in The Starry Messenger, a sensational book that made him a celebrity across Europe. But his advocacy for the Copernican system put him on a collision course with the Catholic Church, which saw it as a direct challenge to Scripture. In 1633, he was tried by the Inquisition, forced to recant, and spent the rest of his life under house arrest. The battle between authority and evidence had been joined. While Galileo looked outward, the French philosopher René Descartes looked inward. Traumatized by the religious wars tearing Europe apart, Descartes sought to build a system of knowledge based on certainty, not on the conflicting opinions of ancient authorities. He began with radical doubt, rejecting everything that could possibly be doubted. The one thing he could not doubt was his own act of thinking. This led to his famous conclusion, cogito ergo sum. I think, therefore I am. From this foundation, he rebuilt knowledge, envisioning a universe that was a vast mechanical system operating according to mathematical laws. He saw the human body itself as a machine. Descartes' mechanical philosophy and his faith in rational deduction provided a new framework for understanding the world, separate from theology. The revolution reached its spectacular climax with a reclusive, obsessive Englishman, Isaac Newton. In 1687, Newton published his Mathematical Principles of Natural Philosophy, arguably the most important scientific book ever written. In it, he presented a universe governed by a single universal law, the law of universal gravitation. The same force that caused an apple to fall from a tree kept the moon in orbit around the Earth and the planets in orbit around the sun. To prove this, he invented a new form of mathematics, calculus. He formulated his 3 laws of motion, which described how every object in the universe moves, from a rolling cart to an orbiting comet. Newton had synthesized the work of Copernicus, Kepler, and Galileo into a single, breathtakingly powerful mathematical system. He had shown that the same physical laws operated in the heavens as on Earth, uniting the cosmos into one coherent whole. He was not just explaining nature, he was revealing its deepest, most hidden language. Underpinning this entire transformation was the development of a new methodology, the scientific method. Pioneered by Francis Bacon, it emphasized systematic observation, experimentation, and inductive reasoning. Knowledge was to be built from the ground up, from careful experiments whose results could be verified by others. This was a direct rejection of the Aristotelian method, which relied on logical deduction from first principles. The creation of institutions like the Royal Society in London provided a forum for scientists to share and critique each other's work, creating a collaborative community dedicated to the gradual, collective advancement of knowledge. The legacy of the scientific revolution is our modern world. It replaced a world of mystery and superstition with one of natural law and predictability. It gave us the tools to understand and eventually to master our environment, paving the way for the technological advances of the Industrial Revolution. It shifted authority from ancient texts and religious dogma to evidence and reason. The courage of these thinkers to question everything, to trust observation over authority, and to seek mathematical descriptions of nature created the foundation for all of modern science. They taught humanity to be humble before the evidence and ambitious in its quest for understanding. The scientific revolution was the moment we stopped believing we were at the center of everything and started trying to understand our true place in an astonishingly vast and complex universe. It was the moment we grew up,